Okay, so welcome. This is the first section of Chapter 2 on describing, or Chapter 2 is on modeling distributions of data. As we go through this, you should follow along in your book because I'll be referring to it and take notes in your packet and, of course, ask questions at the end. There will be some times at the during this discussion where you should pause the video and practice the example problems that we're going to do. Okay, so let's get going here. So in section 1, we're going to be describing the location in a distribution. We're going to talk about the percentile, which you should be familiar with. We're going to estimate percentiles and individual values using a cumulative relative frequency graph, which we'll learn in this section. And we're going to find and interpret the standardized score and describe the effect of adding and subtracting, multiplying, and dividing a constant by the spread and center and shape of a distribution of data. Okay, so this starts on page 83 of your book. I'm actually starting on page 84. So let's talk about percentiles. So one way to describe the location of value in a distribution is to tell what percent of observations are less than it. So we talk about the percentile. So the pth percentile of a distribution is the value of the p% of observations less than. So the key word in that is so let's say on a test you got 92%. That means there are 92% of all the scores that are lower than yours. And you'll see how that works when we get there. So here's an example. So Jenny scored 86 on her first test in statistics. How did she perform relative to the rest of the class? I'll let you ponder that for a moment. Pause if you need to. So here's a stem plot of the scores on the test. And of course, the key is not shown, but the numbers on the left represent the tens. So this would be 72, 73, 73, 74. So Jenny's score is right here in the 86 on the test. Now we don't know whether that's out of 100. We don't know whether that is out of 87 or anything like that, but just this raw score of 86. So how well did she perform on this test relative to the rest of the class? Well, since how there are 3 scores above her, the 89, the 90, and the 93, her score was greater than 21 out of the 25. So hers is the 22nd score. So there are 21 of them that are below her. So we're going to calculate the percentile. So we take the 21 out of 25 that are less than hers, and that equals 84%. This means that Jenny is at the 84th percentile in the class test results. So how well did she do? Well, she did pretty well because the most of the class was below her. And those are all the red scores and right there that are below hers. So on page 85 of your book, it shows you those scores and then the stem plot and then this percentile or this example problem is on page 86 of your book. So let's take a look at those, which is not on this. I don't have the screen on. So Norman, who scored 72, you can see the solution on that computed as the 72 is right there. There's only one below his, so we calculate that as 1 out of 25 or 4% relative to the rest of the class. Katie, who scored a 93, so she's at the, there are 24 below hers, so she's at the 96th percentile. Why isn't she at 100 percentile? Well, we'll talk about that later. Now, there are two students who scored 80, right there, 80 and 80. And there are 12 below them. And so they scored at the 48th percentile because there's 12 out of 25. So to get the percentile, you simply figure out how many scores are below the score you're focusing on, and then you calculate that as a percentile. Okay, so the next topic is the cumulative relative frequency graph. Let's break that apart. A graph, of course, is a graphical way of representing data. A frequency graph means that it shows how often something occurs on the graph. Relative frequency means that how often something occurs relative to the group, and cumulative means that we're adding it all up. And you see how that works. A cumulative relative frequency graph displays the cumulative relative frequency of each class of a frequency distribution. Understand that class is the group that you're looking at, so 0 to 10 or 10 to 20 and things like that. To calculate the relative frequency, we're going to have to calculate that when we take the count and we divide that by the total of the score, the total of the number of scores. The cumulative frequency means we are what the count is from the beginning, so we're going to add them up. And the cumulative frequency, relative frequency, is we take that cumulative frequency and we divide it by the total. So let's go ahead and look at the data that you have on your packet. This example comes from page 87, and the data is there for you. So you can see that this is the age of the first 44 presidents when they were inaugurated. And so it shows us the classes of 40 to 44, 45 to 49, and so on. So these are the classes that they break the frequency table up into. And then they count how many those scores are, and that data is on page 86, 87. And so you see 2, 7, 13, 12, 7, and 3. Now, to get the relative frequency, we are going to take the frequency and divide that by 44. If you need to pause the video, you can calculate that. Okay, so we have 4.5% in that class, 15.9% in 45 to 49 class, and so on. So we have the things. Now, to get the relative frequency, we're going to take this, or rather the cumulative frequency, we're going to count from the beginning. So now we're going to go back to counts, and from the beginning, which is the lowest class is 40 to 44, you're going to just count up. You're going to add up this column as you go. So you can pause the video if you need to. And so we get this cumulative frequency. So we have 2 up to this point, and then we add the 7 for 9 up to that point, then 22, 34, 41, and 44. Because we're going to use that to get the cumulative relative frequency. So that we do by taking this column, cumulative frequency, and dividing it by the total. The total number is, once again, 44. You may pause and calculate that, fill out your table. Okay, so here we have 4.5% in the first class, 20.5 because we're taking the 9 divided by 44, and so on. So that by the time we get to the top, where we had 44 in the last class, we now have 100% of the scores accounted for. What we're going to do with that now is we're going to make a graph out of it. And so you have the axes on your paper. So we have the 40 to 45 and so on. So we don't have this going from 0, but we do have the cumulative relative frequency going from 0. So now we're going to take the 4.5 and we're going to graph that above, and then the 20.5 and so on. So go ahead and fill out your graph, pause the video. So it ends up like this. So from 40 to 45, it went up to 4.5%. We don't know, how exactly, but we just do a straight line for that. 45 to 50 went up to 20.5, then to 50% exactly, and then the 77.3, 93.2, and 100. So you can see how the data goes, that it sort of increases slowly, then increases steady, then slows down and increasing also. Okay, so we're now going to take that and not do anything with it. No. Let's try an example problem, or we're going to do the exercise on page 100. So if you go in the end of the chapter where the exercises are, rather the end of the section, my mistake. And then we're going to look at problem number 9. Okay, so this has to do with shopping spree. It says the figure below is a cumulative relative frequency graph. So here's what the graph looks like. You might want to look at it on your paper or your books so it's clear. By 50 consecutive grocery shoppers. So evidently they polled 50 people at the register, and this is what they spent. So we don't have a data table on this, so we have to trust this cumulative relativity. So first question is we're going to estimate the interquartile range. And the interquartile range is calculated, if you recall, by taking it's the in between the 75th and 25th percent. So you think about a box graph, right? The middle is the medium, and the left is the Q1, and the right is the Q2. And that box represents the interquartile range. So we are going to estimate that. So how do we figure out what these two percentages are? Well, we use the cumulative relative frequency here, and we draw a line over from the 25 and then down to the amount spent. Same with the 75. So this looks like it's just under 20, and this one's between 40 and 50. Eyeball it the best you can. Use a straight edge so that you can draw straight lines. And I came up with 46 for the 75th percentile and 19 for the 25th percentile. So the interquartile range is $27. It's those two. So you can this graph becomes useful because you can get that statistic from there. Next question is what percentile is 1950? So that one's pretty simple, right? $19.50. We go over to where that's at. We draw a line horizontal, or vertical rather, and then over to the horizontal axis. And so it looks like it's between 20 and 30. So that ends up to be approximately 28th percentile. So once again, pretty useful. Now we're going to draw a histogram from this. So to get a histogram, we need to fill out this table. We have the 0 to 10%, so we read the end of the class. So 10% is about 6%. The end of the 20 is about 28, and then 55, and so on, so that we have all the way to 100%. But that's not what we're going to make the histogram about. We need to have the relative frequency in order to do that. So now we just go backwards what we did before, and we start with the 6%, and then between 6 to 28 is 22, between 28 and 55 is 27, and so on. So then we have it how the difference in each of the things. You maybe could have just done it straight from this graph and figured out how much it went vertically between each of the data points. Okay, and now we're going to make a histogram out of this. So we take these classes, we set it up on the horizontal axis, and then we use a relative frequency. It doesn't look like it has to be very big because it only goes up to, the biggest one is about 20, is 27, so we don't have to have the axis very high. And so we end up with this histogram that looks like this. 0 to 10 goes up to 6, and then 10 to 20, and so 22, and so on. And so you can see how the first problem, we went from data, or we can go from histogram to cumulative relative frequency, and then now we can go backwards. Okay, so that's the cumulative relative frequency idea. And so let's take a look and see what's next. Okay, so now, and you can take a look at 89, and you can either pause and look at 89 and see, check your understanding. It's got questions and answers there on that for you to check to make sure you understand. The next topic is about measuring position. So now we're actually going to be able to measure the position. When we say measure, then mostly we're going to do what's called, a calculation. And so we're going to look at something called the z-score. And the z-score tells how many standard deviations from the mean an observation falls, and in what direction. So the reason it's called z-score is because it comes from the word standardized, and so I made that big in there. And the z-score is, if we want to figure out how many standard deviations, then we need to have the difference between the score that we're looking at. This is called the observation, and we subtract the mean and then divide it by the standard deviation. It'll tell us how many of those. So you understand, we're going to get a number, a small number, 1 standard deviation, 2, 3, 4, not much, rarely do we go above 4 on z-scores. So an example would be back to Jenny and her 86. So we have to know what the class mean was, and that would be 80. We could have gone back and calculated that from the data, as well as the standard deviation. We learned how to do that in chapter 1. But here it is, the mean of 80 and standard deviation of 6.07. So what is her standardized score? You may pause if you just want to calculate it. We're going to start with the formula above. And so we plug in the observation, which is going to be 86. The 80 is the mean, and the standard deviation is 6.07. And so by calculating that, you may pause and calculate. You get 0.99. Well, what does that mean? What does that mean? Remember, the z-score tells us how many standard deviations. So this means that Jenny's score is almost 1 above the mean, because it's 0.99. If it was negative, then it would be below. So that's called the z-score, and we calculate that for the standard deviation. Okay, so let's go ahead and do an example. Let's look at Eleanor and Gerald. This is from page 101 in your book, and it is about taking the SAT and the ACT. Number 11. So Eleanor scored 680 on the SAT, and that SAT had a mean of 500 and a standard deviation of 100. Gerald scored a 27 on the math portion of the ACT, which has a mean score of 18 and a standard deviation of 6. So who scored better? So with this, we can calculate the z-score of each, and that will tell us how many standard deviations their score is from the mean. So go ahead and pause and do that. So Eleanor's was 680 minus 500 over 100, and hers came out to 1.8 standard deviations. And the z-score of one of Gerald is 27 minus 18 over 6. and that is 1.5 standard deviations. So now, I say that Eleanor scored better by 1.8 above. Hers is 1.8 above the mean, and Gerald is only 1.5 above. So that means she scored higher. The more you are, the more positive number of standard deviations you are above, then the better you did. If both of these were negative, then of course Gerald would have scored better. Okay, so hopefully that you understand that. You can take a look at the check your understanding on page 91. The next topic in this section is about transforming data. And this one's pretty straightforward. This has to do with, we have some data of a group of students who guessed the width of the room in meters. And the story goes along, in Australia, they were changing from English measurements to metrics. And so a teacher had the students guess how wide the classroom was. And so the data right here, this dot plot shows you the score, the measurements. The range is from like 9 meters up to 40 meters. And let's go ahead and describe this data. How would we describe the shape of this data? Well, it is bimodal. It has 2 peaks. And because of these scores, single scores out here, we call it skewed right. How about the center? And refer to page 92, and there is a table underneath this data from a program called Fathom that crunches numbers, and you can see from that what the center is. So we either are going to talk about the median or the mean. So we'll go ahead and list both of those. The median is 15, and the mean is 16 meters. And so you can see how that is. In this case, we have X bar. 16.02 is actually the mean. What about the spread? Well, whenever we're talking about the median, then of course we use the IQR. So we also get that from the data table. And so the IQR is 6, and the standard deviation is 7.14. So mentioned right here, the median is better because it is skewed data. If all this data was crunched over there, then maybe the mean would be better to talk about, but because we have all that data out to the right. Outliers, you should remember how to calculate outliers, and that's going to be, we take 1.5 times the IQR, so it's 1.5 times 6. We add that to the first quad, the Q1, and we add that to the third quartile, which is 17, so we get 26, and we subtract that from the first quartile, which is 11, so we get 2. And then we look to see if we have any data. Well, we do have some data. It looks like the 27, 35, 38, and 40 would all be outliers. No outliers down below here, because that comes out to 2 would be the edge of what the outliers are. Okay, so first off, that was just a little practice on describing data from last chapter. So when we're transforming data, we're taking some data and we are moving it. Transforming means to move it. And so the students guessed on the width in meters, and so we examined the distribution of guessing errors by defining a new variable. And so we can now calculate the error, and we take the guess and we subtract the actual. Well, the actual in this case was 13 meters was the width of that classroom, and so we're going to subtract 13 from every one of our data points. So what does that do to the data? Well, here's what it looks like now. Everything shifted over. So what about let's describe it again. Let's talk about what it changes. Did it change the shape of the data? No, still bimodal, still skewed to the right. Did it change the center? Well, yeah, it moved the center over to the left, both for the median as well as the mean. And what about the spread? No, spread is still the same, right? It's still the difference between the maximum and minimum, as well. However, when we calculate, so the range doesn't change, but when we're talking about the standard deviation, the IQR, the numbers are going to be the same. So the spread doesn't change. And what about outliers? No, it doesn't change the outliers either. And so the table on page 93 has all these numbers in it. You can see that from the data. So the mean, it went down 13 on the error. Standard deviation stayed the same. The minimum shifted. The Q1, median, and Q3 all shifted by 13. The maximum shifted. The IQR stayed the same, and the range stayed the same. So some things, when we add or subtract, are changed, and other things are not. So transforming converts the original to original units, from the original units to another scale. The transformations affect these things. So some things stay the same. So if we add or subtract a number A, then the measures of central location, the mean, median, quartiles, percentiles, also adds, but doesn't change as the range, the IQR, and the standard deviation. And rather than memorize these things, it's probably best if you just figure it out each time by imagining what's happening. All right, so here's another twist on this example. And now I'm on page 94. Because our group of Australian students is having some difficulty with the metric system, may not be helpful to tell them that their guesses tended to be about 2 or 3 meters too high. Let's convert the error data to feet before we report back to them. So they're roughly 3.28 feet in meters. I'm not going to actually have you do this, but let's take a look at what happens to the data when we convert to using the 3.28 factor. Then we are going to multiply each by 3.28. So what happens? Rather, dividing by 3.28. So what's going to happen to the data? Well, you see the numbers are sort of crunched in from the right in here, right? Actually, I'm looking at the wrong one. We are multiplying. So we're going from this error in meters to feet. So we're multiplying by 3.28. So it kind of spreads the data out. So we have data, and now the maximum's way out here, 3 times as much as it was there. How does this end up to be crunched to the left? Well, that's because these are negative numbers, and when we multiply by a negative number, then it crunches it in a little bit, or it spreads it out, right? So we're going from here to here. So we're just spreading the data out. So what happened overall? Well, the mean shifted, right, from meters to feet. So it goes up by a factor of 3. So that increase. Standard deviation also 3 times. About. Minimum now has been shifted. The Q1 shifted by 3. I'll multiply by 3. And so everything is multiplied by 3. So everything changes when you're multiplying or dividing. Okay, so in summary, then when we're transforming data by multiplying to dividing, when we multiply each observation by the same number B, it also multiplies the center and the location. And when we divide or multiply by B also, then the IQR it also multiplies the measures of spread. So everything multiplies at that point. Okay, so, and it doesn't change the shape. So in this section, we certainly talked about how we find percentile, and then we estimated percentiles and used a cumulative relative frequency graph. We found and interpreted z-scores, so that's a calculation you need to know how to do. And then we described the effects of adding, subtracting, multiplying, dividing by a constant on what happens to the shape, center, spread, and distribution. The only thing that doesn't change when you're multiplying is the shape. Okay, so some practice problems for you to do, and I will check that next opportunity. If you have any questions, send me an email. All right. Thank you for listening.